Have you ever wished you could test out a new idea without any real-world consequences? What if a car manufacturer could see how a new engine design performs before building a single prototype? Imagine a city planning team predicting traffic flow changes before constructing new roads. Or how about being able to solve urgent problems as they happen with pinpoint accuracy? Imagine a factory experiencing unexpected downtime. How do you quickly figure out what's wrong and fix it? And what if we could predict the impact of a natural disaster before it strikes? Could we simulate the effects of a hurricane on a coastal city, or see how an earthquake might affect critical infrastructure? Imagine having the ability to prepare for the worst, even before it happens. How much safer could our world become? Turns out, there's a way to make this possible. We can create virtual replicas of physical systems to simulate and analyze real-time data, letting us predict failures and fix issues as they happen. These replicas help foresee maintenance needs, optimize performance, and even prepare for natural disasters. This cool technology, known as digital twins, is changing how we tackle complex problems and come up with innovative solutions across different industries. In this video, we'll dive into the fascinating world of digital twins and explore how this technology is revolutionizing everything from manufacturing and city planning to disaster preparedness. We'll break down the different types of digital twins, the key components that make them work, and the essential requirements needed to create these powerful virtual models. We'll also take a look at how digital twins are shaping the future, opening up possibilities we've only just begun to imagine. So, without further ado, let's dive in. Chapter 1: The History of Digital Twins. The story of digital twins starts with a notion that predates the term itself, creating virtual replicas of physical systems to understand and improve them. This idea, while still in its infancy, began to take shape in the 1960s as engineers and scientists grappled with the complexities of aerospace and manufacturing. The origins of what we now call digital twins can be traced back to the early days of computer simulation and modeling. Engineers at NASA, in particular, were among the pioneers who saw the potential of using simulations to mirror real-world systems. One of the earliest examples of a digital twin in action was during the Apollo missions. It's April 11, 1970, and Apollo 13, the third mission intended to land humans on the moon, has just launched. The mood is optimistic. The crew, Jim Lovell, Fred Hayes, and Jack Swigert, are on their way to make history. But just 2 days into their mission, something goes terribly wrong. On April 13th, as the spacecraft hurtles through the cold expanse of space, Swigert hears a loud bang followed by an unsettling vibration. The words he radios back to Mission Control in Houston become instantly famous. "Houston, we've had a problem." An oxygen tank had exploded, crippling the spacecraft. Their moon landing dreams were dashed, and now it was a race against time to bring the astronauts back home alive. Here's where it gets fascinating, especially when we talk about the idea of digital twins. While Apollo 13 didn't have what we'd call a digital twin in today's tech language, it had something close, an analog twin, if you will. Down on Earth, NASA had an exact replica of the spacecraft, complete with all its systems and quirks. They used this replica as a part simulation training before the actual launch. When the explosion happened, the engineers and scientists at NASA's Mission Control immediately started working with this Earthbound twin. They recreated the conditions the astronauts were facing, troubleshooting problems in real time. This hands-on, rapid problem-solving was crucial. For instance, they figured out how to rig a makeshift carbon dioxide filter using spare materials aboard the spacecraft, a process that was first tested on the ground. The communication between Mission Control and the astronauts was a lifeline. Each transmission was critical, laden with technical details and precise instructions. The astronauts, under the immense pressure of their life-threatening situation, relied on the calm, methodical guidance from Earth. Every adjustment, every procedure was first tested on the twin before being relayed to the crew. Engineers in Houston continuously ran simulations on the analog twin to anticipate the spacecraft's power needs and manage the limited resources. They tested power-up sequences for the command module, which had been shut down to conserve energy, ensuring that when it was time to re-enter the Earth's atmosphere, the systems would function as needed. In the end, the successful return of Apollo 13 was a testament to the ingenuity of the use of an Earthbound twin, the precursor to today's digital twins, demonstrated the profound impact of simulation and real-time problem-solving in mission-critical situations. As technology progressed, the concept of digital twins continued to evolve. By the 1980s, the rise of more advanced computer systems and the increasing complexity of industrial processes led to the development of more sophisticated simulation techniques. The idea of creating virtual replicas to test and optimize systems gained traction in various fields, including manufacturing and engineering. This period marked the beginning of a broader application of the concept beyond aerospace. One of the significant milestones in the evolution of digital twins came in the early 2000s, when the term itself was coined and formalized. Michael Greaves, a professor at the University of Michigan, is often credited with popularizing the concept. Greaves introduced the term digital twin during a presentation at a computer-human interaction conference. Chapter 2: Modern Digital Twins. In today's world, digital twins have evolved into powerful tools that bridge the gap between the physical and digital realms. McKinsey defines a digital twin as a dynamic, virtual representation of a physical asset, process, or system that is continuously updated with real-time data and uses advanced analytics, artificial intelligence, and machine learning to simulate, predict, and optimize performance. Think of them as virtual copies of real objects or processes. Detailed and interactive models that let you explore and analyze them in ways that were once impossible. Unlike static models, modern digital twins are dynamic and updated in real time, behaving and evolving just like their real-world counterparts. A digital twin comprises three key components that work together seamlessly to create this robust connection. First, there's the physical object or process itself, embedded in its natural environment. Think of a manufacturing plant, an airplane engine, or even an entire city's infrastructure. Second is the digital representation of that object or process. This isn't just a simple 3D model, it's an intricate simulation that incorporates vast amounts of data to replicate the physical entity's behavior and performance. And third, connecting these two realms is the communication channel, often referred to as the digital thread. This is the lifeline that ensures continuous data flow between the physical and digital twins. It enables the digital twin to update in real time, reflecting any changes or anomalies in the physical world. This constant feedback loop allows for ongoing monitoring, analysis, and optimization. There are various types of digital twins, each serving different purposes. For instance, product twins are used to design, test, and optimize new products before they are manufactured. They allow engineers to run simulations and make adjustments without the cost and time associated with physical prototypes. Process twins focus on replicating and optimizing operational processes, such as those found in manufacturing, supply chains, or logistics. These twins help improve efficiency, reduce downtime, and enhance overall performance. System twins, on the other hand, encompass entire systems or ecosystems, such as smart cities or energy grids. They provide a holistic view of interconnected components, enabling better management and coordination. The applications of digital twins are as diverse as they are impactful. In manufacturing, digital twins enable predictive maintenance by monitoring equipment in real time, identifying potential issues before they cause failures, and scheduling timely repairs. This not only reduces downtime, but also extends the lifespan of machinery. In healthcare, digital twins of patients can simulate treatment plans and predict outcomes, leading to more personalized and effective care. Urban planners use digital twins of cities to model traffic flow, optimize public transportation, and design more sustainable and resilient infrastructures. In the realm of smart buildings, digital twins monitor energy usage, optimize lighting and HVAC systems, and enhance occupant comfort while reducing operational costs. The automotive industry uses digital twins to design and test vehicles, simulate driving conditions, and develop autonomous driving technologies. Thanks to advancements in 3D graphics technology, the creation and use of digital twins have become more practical and widespread. Modern 3D graphics technology enables the detailed and accurate representation of physical objects and environments in a digital format. One of the key innovations in this field is the development of high-performance graphics processing units, GPUs. They are essential for managing the vast amounts of data and complex calculations required to render lifelike digital environments. Nvidia's RTX series, for example, includes dedicated ray tracing cores that enhance the realism of graphics by accurately simulating the behavior of light. This is crucial for creating digital twins that not only look realistic but also behave in ways that mimic their real-world counterparts. Additionally, software platforms like Autodesk Maya, Blender, and Unity play a crucial role in building and refining 3D models for digital twins. These tools offer advanced modeling, texturing, and rendering features, with physics engines like Nvidia's physics integrated to simulate real-world physical phenomena such as gravity and collision. Advanced rendering techniques, including physically based rendering, PBR, and global illumination, further enhance realism by accurately depicting how light interacts with surfaces and environments. Real-time rendering engines like Unreal Engine and Unity provide immersive visualization and interactivity, while machine learning and AI optimize rendering processes and simulate complex behaviors. And there are dedicated platforms like Nvidia Omniverse. Nvidia Omniverse offers a collaborative environment where developers, designers, and engineers can work together in real time, using photorealistic simulations to build and refine digital twins. From sophisticated hardware and software integration to powerful engines and cutting-edge generative AI, it provides a comprehensive platform that seamlessly blends technology to create highly accurate and dynamic digital representations. The Internet of Things, IoT, artificial intelligence, AI, machine learning, and cloud computing also play the role. IoT devices equipped with sensors collect and transmit data from the physical object, which is then processed using AI and machine learning algorithms. These algorithms analyze the data, generate insights, and continuously update the digital twin to ensure it remains an accurate reflection of the real world. Cloud computing provides the necessary infrastructure for storing and processing the massive amounts of data generated. It enables scalability, so whether you're dealing with a single machine or an entire smart city, the digital twin can handle the data load. Chapter 3: Real-World Use Cases. There are some exciting digital twin projects happening right now. At Siemens, their factory floors are buzzing with more than just machinery. They've created a virtual copy of their entire production line, allowing engineers to tweak and test scenarios in real time without stopping the machines. This helps boost efficiency, cut downtime, and improve product quality. In healthcare, Philips Healthcare is using digital twins to personalize patient care. Doctors now have a digital version of each patient, which replicates their unique biology. This lets them test different treatments and predict outcomes more accurately. Philips also uses digital twins to monitor and maintain medical equipment, spotting potential issues before they cause problems, which keeps everything running smoothly and safely. In the automotive world, General Motors, GM, uses digital twins to design and test new cars virtually. Before building any prototypes, they create a digital model and run it through performance, safety, and durability tests under various conditions. This speeds up development and cuts costs by reducing the need for physical prototypes, helping GM innovate faster and stay ahead in the competitive automotive market. Across the globe, in the vibrant city-state of Singapore, the entire urban landscape has been transformed into a digital twin. This isn't merely a collection of static maps, but a living, breathing digital representation of the city. Urban planners now have the power to simulate traffic patterns, forecast energy usage, and plan emergency responses with unprecedented accuracy. They can visualize the impact of new infrastructure projects, optimize public services, and create a more sustainable and livable environment. Imagine scaling this concept to the entire Earth. That's what Nvidia does with their Earth 2 project. This ambitious initiative aims to create a comprehensive digital twin of our planet, integrating real-time data from satellites, sensors, and IoT devices. By simulating everything from climate patterns to urban development, Earth 2 could revolutionize how we understand and interact with our world. Scientists could predict natural disasters with greater precision, governments could implement more effective environmental policies, and businesses could optimize supply chains by anticipating global trends. Essentially, Earth 2 would serve as a dynamic, interactive model of our planet, enabling us to make more informed decisions for a sustainable future. Chapter 4: Challenges. While digital twins hold immense promise, they are not without their challenges and shortcomings. One significant hurdle lies in the complexity and cost of implementation. Creating an accurate and functional digital twin requires a substantial investment in sensors, data collection infrastructure, and computational resources. For industries operating on tight budgets, such as small manufacturers or municipalities, these costs can be prohibitive. Additionally, the technical expertise needed to develop and maintain digital twins is not always readily available, further complicating adoption. Data integration is another critical challenge. Digital twins rely on continuous streams of data from a multitude of sources, including IoT devices, legacy systems, and third-party applications. Ensuring seamless integration and interoperability between these disparate data sources can be a daunting task. Inconsistent data formats, communication protocols, and security measures can lead to gaps in the data stream, undermining the accuracy and reliability of the digital twin. Moreover, data security and privacy concerns loom large. The data fed into digital twins often includes sensitive information, whether it's proprietary industrial processes or personal health data. Ensuring this data is protected from cyber threats and unauthorized access is paramount. However, the more interconnected and data-rich a system becomes, the more vulnerable it can be to cyber attacks. Scalability also presents a significant challenge. As digital twins evolve from single assets to complex systems of interconnected twins, sometimes referred to as digital twin ecosystems, the computational and data management demands increase exponentially. Managing the data flow, computational load, and real-time updates for such large-scale systems can strain existing IT infrastructure and require substantial upgrades and optimization. Chapter 5: What's next for digital twins? Despite the significant challenges to the widespread adoption of digital twins, it could very well become the next major revolution. Emerging trends already point towards the use of digital twins in new and unexpected industries. Agriculture, for instance, stands to benefit greatly from this technology. Digital twins of farms could monitor soil conditions, crop health, and weather patterns, enabling farmers to optimize irrigation, fertilization, and harvesting processes. This not only increases yield and efficiency but also promotes sustainable farming practices by minimizing waste and resource use. In the realm of environmental conservation, digital twins could play a pivotal role in preserving ecosystems and combating climate change. By creating digital replicas of forests, oceans, and other natural habitats, scientists can monitor changes in real time, predict future impacts, and devise strategies to mitigate damage. The impact of digital twins on innovation cannot be overstated. As the technology becomes more accessible and affordable, we will see an explosion of creativity and experimentation. Startups and small businesses, in particular, will find new ways to leverage digital twins to develop products, streamline operations, and enter markets more rapidly and efficiently. If you made it this far in the video, comment with the word AI to let us know you're tuned in and receiving all this information. To stay ahead in the age of AI, don't forget to check out our other videos on the channel. We cover everything from the latest tech trends and how to leverage these advancements in your own projects. And, of course, make sure to subscribe for more insightful content that keeps you at the forefront of innovation. Thanks for watching.